Hi, I'm going to talk about emerging technologies in embedded system design. In today's presentation, I will use several slides and white papers that are publicly available on the internet. I acknowledge the original authors of the slides and white papers, and I do not claim any copyright to these materials. Any usage and dissemination of this lecture must adhere to the original copyright notices. I will talk about emerging technology in embedded system design from three aspects: hardware, software, and design methodology. In the hardware perspective, I will talk about system on chip and also open hardware. In the software perspective, I will talk about embedded OS represented by Android. Also, in the hardware perspective, I will talk about embedded applications in healthcare, e-commerce, etc. I will talk about Internet of Things and intelligent systems. And follow that, I will talk about open embedded projects. In the design methodology perspective, I will touch upon full system simulation using CIMIX. System on chip. System on chip is to integrate all components of a computer into a single chip. For example, in a system on chip design, you may have processor cores, could be an ARM core, MIPS core, or x86 core. In addition to the cores, you may see digital, analog, mixed signal, radio frequency, digital signal processing coprocessors on the same chip. This system on chip design is much more powerful than conventional simple microcontrollers. With this system on chip design, this chip you can connect to external memory such as flash or RAM. Also, you can connect this chip to other peripheral interfaces such as USB, Ethernet, SPI, I2C, and these interfaces could be on chip as well as off chip. And this system on chip design, which are oftentimes much more powerful than conventional microcontrollers. That is to say, these processors are capable to run embedded operating system, such as Linux or embedded Windows, and they may execute many applications that rely on network stack and databases, etc. Here is an example system on chip design. This is the Intel Atom Z2580 chip. As you can see, this is the diagram, functional diagram of the chip. In this chip, we have CPU cores, and in this case, it's an x86 core. And we have caches for supporting the core. And in addition to those, we have different coprocessors, for example, 2D, 3D graphics, video decoding, video image enhancement, and video decoding. Also, it has image signal processing, which is programmable. Also on this chip, you have security programmable execution environment and crypto engine. To connect this chip to other peripheral interfaces, they have built-in I/O interfaces such as SPI, UART, etc. This chip can also connect to different memory interfaces such as DDR2 or flash memory. This is another example of system on chip. In this case, it's based on ARM processor core. To connect it to this core, it has this internal bus, which is connected to different controllers, such as interrupt controller, power management controller. Also, this chip core is connected to different peripheral interfaces, such as Ethernet, UART, SPI. Also inside this chip, it has a small amount of SRAM and flash memory, and they are controlled by this memory controller. Now I'm going to talk about open hardware platform, Beagleboard. Beagleboard is an open hardware platform designed by TI, Texas Instrument, using a TI ARM-based processor. And this set of presentation was presented by Jason Quittner in 2011 at Embedded System Conference at Boston. So what is a Beagleboard? Beagleboard allows you to bring your own peripherals. It has very low cost, and it's an ARM-based processor, and it has graphics and DSP processors, and supports Linux and other open source tools. It's a small environment for innovations. This is the Beagleboard XM. Beagleboard actually has a different type of boards. Some are big like this, some are even smaller. Those are credit card size. This board is a little bit larger. This board is based on this ARM Cortex-A8 processor from TI. It can run about 2,000 million instructions per second. It can support about 20 million polygons per second for graphics processing. It is capable of doing HD video encoding and decoding. So this is the processor itself. Also, inside this processor, this actually is a package. It has 512 megabytes of DRAM. Talking about interfaces, it has a lot of different interfaces: LCD, I2C, DVI-D, S-Video. It has 100 megabits per second Ethernet. It supports USB 2.0. As you can see, this little board is packed with a lot of processing power and a large set of peripheral interfaces. So some Beagleboard usage example: you can do a video encoding and playback. You can do 3D rendering. Also, you can stream and process data from peripherals. It's fairly easy to get a Beagleboard up running. It comes with the SD card with a default Angstrom Linux distribution. It can also run Ubuntu, Linaro, and Robot, which is a TI provided Linux distribution. And it's meant for classroom usage. You can easily attach the Beagleboard with LCD, with keyboards. You can use it as a small computer, but in fact it has a very small form factor, consumes very little power. Depending on the Linux distribution you have, you can have different GUI. If you run a Robot, it's an Android-like distribution. You can actually have this type of interface. If you run Ubuntu, you can have the typical GNOME or KDE desktop interface. The processing power of this processor is pretty intensive. It runs at 1 gigahertz. It can support a very nice desktop environment. This is the GNOME desktop that you can run on top of this little board. This is Angstrom distribution. It has different styles you can change. You can also show the processor frequency, which is 1 gigahertz, as you can see here. You can change the GUI menu by changing the configuration file. Now, this Beagleboard is released as an open hardware, which means that the hardware design of this board, the schematic, the layout, the bill of materials are all public. So you can literally using the schematic and using your PCB software to lay out the board and build a new one. Of course, during the process, you can change the design and adding or remove some of the components to fit your application. So it's designed to work with the open source community. The purpose is for faster innovation, so the development cycle time is shorter. It also can support direct peer interaction because a lot of people have been working with this board, and people share their experiences. Also, with this open community, you can have better solutions. As you can imagine, that many experts can jump in to give you comments and to provide peer review and provide early feedbacks. The Beagleboard has its own source code packages, which is being pushed to the mainline Linux. This is for stable snapshot development to increase stability and provide updates. You can ask questions online to find answers from other experts, and you will need to go to appropriate forums to ask your questions. For example, you can do online chat or using mailing list. Here is the typical Beagleboard XM boot process. First phase is the ROM, the read-only memory loads xload, which is a very small startup code in format of MLO. And then this xload loads the U-boot, which is the bootloader of the board. And the U-boot will execute default environment commands. For example, using the script for U-boot, you will specify where is your kernel location, and also what is the environment variables, such as the serial console speed, the monitor resolution will be specified in this uenvironment.txt file. And the next step is to load the kernel from the root device you specify, and the last step is that the kernel will start and reach the root file system. This is an example of default uboot boot command. As you can see, it specifies the sequence to scan the device, MMC device or SD card device, and then where to load the environment variable and how to load the kernel images. The baseline software includes the xloader, uboot, Linux kernel, and also various BSPs to support the different peripherals, the devices on the board. Intel Galileo is also an open hardware platform. This little board is just released, and it's based on Intel Quark SoC X1000 application processor, which is essentially a 32-bit Intel Pentium class system-on-chip processor. This Galileo board is the first board based on Intel architecture designed to be hardware and software pin compatible with Adrenal shield designed for Uno R3. This is the picture of the board. This is the front and this is the back. As you can see that this little board has an Intel processor here, and also is packed with different peripherals that we'll talk about shortly. This little board is designed to support shields that operate at either 3.3 volts or 5 volts. You can change the core frequency to use a jumper to enable voltage translation to 5 volts. And this Galileo board is software compatible with Adrenal software development environment, which makes usable and introduction a snap. This is a diagram of this Galileo board. As you can see that here's the Intel Quark SoC application processor. It has a lot of connections to peripheral interfaces going from here. This is to the DDR memory, and it has a JTAG debug interface. It connects to this mux, which in turn connects to a jumper, actually a socket interface, where we can find this I2C and also GPIO pins. On this side, it has Ethernet interface, and USB connections. What's notable here is that this Galileo board is the first Adrenal board that supports a PCI interface. It has a mini PCIe slot that you can use to connect to other PCI-based interface card. Some details about this board. It has 14 digital I/O pins, which can be configured as input or output using digital write or digital read functions. It has 6 analog inputs with I2C bus and also SPI interface. Standard UART and a in-circuit serial programming header. This pin supports SPI communication as well. Intel architecture. This is the first Intel architecture-based Adrenal interface board. This processor, this Quark SoC X1000, is a 32-bit Pentium class processor. It runs at 400 megahertz. On chip, it has 16 kilobytes of L1 cache and 512 kilobytes of on-die embedded SRAM. It has a Ethernet connector and a full PCI Express mini card slot with USB client and host controller, and as 10-pin standard JTAG header for debugging. As we said earlier, that this is an open hardware platform, so the schematic and also the layout files are all public available. You can download these files from Intel's website. For communication to this board, you can use UART or USB or through PCI Express. The Ethernet is also an option. This Galileo board can be programmed with Adrenal software, and when you are ready to upload the sketch to the board, you can program this board through the USB client port by selecting the Intel Galileo as your board in the Adrenal IDE. There are many interesting and important new applications of embedded systems in different domains. I will just talk about 2 of them, healthcare and e-commerce. In the healthcare field, actually there are a lot of usage of embedded systems. Here's one example, remote patient monitoring. This is one slide from Philips, and it depicts the remote patient monitoring devices that are deployed at a patient's home. For example, as you can see in this picture, this lady is measuring the heart rate, and these little sensors can be connected to the service centers through wireless or wired connection, and the sensor readings from the patient will be transmitted to the central server. Also, as you can see in the picture on the bottom left, this person is measuring the heartbeat. The data related to the service center can be then transmitted to a doctor or other healthcare personnel for further analysis. This is fitness tracking is another interesting application of embedded systems. This picture is a bracelet designed by a company called Fitbit. This is like a little watch you can wear on your wrist, and this device will be able to measure the footsteps that you have during a day, and these footsteps will be correlated with your activity so that using these sensor data, you can estimate the activity that you carried out during a day, and also you can push these data into a device such as a smartphone. There's a corresponding smartphone app that will collect these data and then do tracking and analysis. You can set goals to achieve, and at the end of the day or at the end of a week, you can try to check from these sensor recordings that whether the number of steps you would like to perform has been really achieved. This picture shows another application of embedded systems. This is in the e-commerce domain. What we see here is a very new product which is still in the works. It hasn't been released yet. This is called the coin credit cards. As you can see, this really looks like a credit card. This is what the final product will look like, and this is a credit card size device. It has the magnetic strip on one side of the card. It has a little push button and a little LCD display here. So the idea is to store the credit card information to this single device. Say if you have 20 credit cards or any kinds of cards, you can store the credit card numbers, all of them, all of these numbers, the expiration date and the names into this single device. And the way you use it is that you can just bring this one card rather than bring 20 different cards. So at the place that you want to purchase a service, that you can push this button and to select the corresponding credit card you want to use and just swipe this one device. On the right side, this is the prototype that we can see. It has a very neat design with a very small microcontroller. We don't really know what exact type they use. Here is a LCD display that shows the credit card numbers and the other information, for example, the credit card company name and the expiration date. And here are some other circuits which we don't really know what they're doing. But the point is that with this very tiny little embedded system, you can carry just one card instead of carrying tens of different cards. You can get more information from the vendor of the card, this website, onlycoin.com. Internet of Things refers to the widespread of sensors in many aspects of our life. For example, in a refrigerator, in a microwave, or in your living room, or in your car, there are many different sensors for sensing the temperature, the light intensity, the connectivity, etc. Today, billions of devices are posed to make more than 1 trillion connections, and also in the process generate enormous volumes of data. The idea is to not only deploy these many sensors and not only connect these sensors, but also try to learn from these sensors. This essentially try to learn from this big data which comes from all the sensor data. A huge portion of the growth of big data comes from the intelligent systems. So we would like these sensors or even machines that connected to each other directly and through the cloud, and to make up what is frequently called the Internet of Things. According to the estimate, this billions of connected devices will be intelligent systems, and these intelligent systems represent a market of 4 billion units and more than 2 trillion in potential revenue. But the challenge is, how do we organize these sensors, these machines, and how do we extract knowledge from these machines? And for that purpose, Intel has proposed a so-called Intelligent Systems Network. Here is a picture of the so-called Internet of Things. So you have a lot of sensors and machines connected. For example, you can have intelligent medical devices in a hospital, which can connect to ambulances. You can have traffic cameras deployed on the road, and these sensor data will be used by automated car system. And these sensors can also connect it to the cloud so that we can scale up the number of connections and also distribute the data more easily. The potential of Internet of Things is huge, but we need to discovering the values in these big data. And to capitalize these opportunities, enterprise needs tools and technologies and platforms to convert the data into value-added information. Intel's intelligent systems work is trying to simplify the deployment of Internet of Things and empower customers to extract greater value from the data. This intelligent system framework is a set of interoperable solutions designed to address connecting, managing, and securing devices in a consistent and scalable manner. It provides flexible recipes utilizing scalable off-the-shelf elements and enables vertical specialization. And it will shift resource investment from interoperability to extracting value from data. Within this intelligent system, it features the fundamental capabilities that not only using components from Intel, but also from the other partners in the ecosystem, such as Wind River and McAfee, and these Intel processors supported in this framework include Xeon processors and also on the embedded side the Intel Atom processors. Here is a snapshot of three angles within this intelligent system framework: connectivity, manageability, and security. For example, on the connectivity side, it supports multiple protocols, wired and wireless. Also, it combines other Intel solutions. On the manageability aspect, it has improved reliability, improved system uptime, and also you can do remote power management, and also you can do hardening in terms of protecting of the system from viruses, and also for compliance management. On the security side, it supports platform protection at the BIOS and firmware level. It also supports software protection at the application level. Yocto Project is one of the open embedded projects that has gained a lot of media attention and also interest from different vendors, hardware and software. So I'm going to introduce a little bit about this Yocto project. And these set of slides are from Mark and Bruce, who presented this Yocto project introduction in November 2012. Yocto, the name comes from the smallest unit of measure, equal to 1/septillionth, that's 10 to the power of minus 24. Yocto Project is an open source project with a strong support community. It is not a single project, rather it's a collection of embedded projects and tools. It's a place for industry to publish board support packages as well as application development tools. The key project is the reference distribution build environment. It contains a complete Linux OS with package metadata. It's released every 6 months with latest kernel, toolchain, and package version, and with full documentation. So in one word, it's not an embedded Linux distribution. Rather, it creates tools and an environment that allow you to create a customized Linux distribution for your purpose. The state of embedded Linux, most of the time you do DIY and roll your own or modified traditional distribution. It's getting hard using this approach to do long-term maintenance, and upstream changes are very difficult to track. Also, there are other issues such as licensing issues and support issues. For commercial and community embedded Linux, there are too many competing systems and often come with incompatibility. As a result, using the traditional embedded system design cycle and tools and environment, developers have to spend lots of time porting or making build systems, and leaves less time or money to develop interesting software features. So what does the Yocto project provide? The industry need a common build system and core technology. And BitBlake and Open Embedded are very well known in this field for providing a nice build tool and also provide a set of open embedded Linux support. The benefit of doing this is have this build system and open embedded build system. It is for design, for long-term design, and also for embedded purpose. And these tools provide transparent upstream changes, and also they have very vibrant developer community. As a result, the developers have to spend less time on things which do not make money, and they will have more time to spend on things which they will make money. So who is the Yocto project? It has an advisory board, also technical leadership. It's organized under Linux Foundation. It has individual developers, also companies in embedded hardware design and in chip design, and also embedded operating system vendors. Here's a short list of these members. For example, Texas Instrument, Huawei, Intel, Wind River, Open Embedded, etc. So why should the developer care about this? The Yocto project allows the developer to build a complete Linux system from source in about an hour. And this customized Linux can support multiple cores. It has support for lots of memory, and also it has a fast disk. It starts with a validated collection of software, including toolchain, Linux kernel, and user space applications. In Yocto project, application developers are separate from system developers, and Yocto project support both of them. The members of this project can access to a great collection of application developers tools for performance tuning, debugging, power analysis, and UI, etc. Also, Yocto supports all major embedded architectures: x86, 64-bit of the x86, ARM architecture, PowerPC, and MIPS. And coming soon, MIPS 64 and ARM 64 will be supported. It has advanced kernel development tools, it has layered module to encourage modular development. Overall, Yocto Project provides embedded tools and best practices and also reference implementations. Next, we're going to talk about CIMICs and how we can leverage CIMICs in designing multi-core systems. And these slides are presented by Jacob in Green River. So embedded multi-cores have a lot of advantages because the power efficiency and also the performance. Multi-core embedded processors have gained a lot of traction in getting into different applications and hardware designs. However, the challenge is when you have multiple cores and when you have multi-threaded and parallel programs, it's getting very hard to debug multi-core systems. And because you may have multiple targets, means that you may have in your system different kinds of processors. Also on these processors, you have processes and threads which execute in different contexts. And each context has different code segment, stack segment, and register values. One way to debug a multi-core system is to do on-chip trace. This is to add actual hardware onto a multi-core system to specifically collect the execution traces of different cores within the same processor. It can capture the addresses these cores issued and also the instructions these cores executed. Performance counters can also be added to trace the execution performance of these different cores. Cross-triggering is another approach that we can leverage, and these tracing cross-triggering will rely on the events that are collected in the tracing logic. It can do stop the execution once an event happens or restart the tracing if another event appears. So what we talk about using these hardware resources on the chip to enable this debugging instrumentation tool to support multi-core and large-scale hardware and software design. The cost is substantial because you essentially have additional hardware built in onto the chip, and it consumes too much power and degrade the performance. With virtualization techniques, you can essentially execute multiple virtual machines on the same hardware processor. So you can, instead of having a traditional single OS on a single core, with the virtualization technique, you can have a hypervisor on a single core, and on top of the hypervisor, you can actually execute multiple and even heterogeneous operating systems. So one could be Linux, one could be a Windows operating system. So with this hypervisor, you can have a very complex system where you have different cores and running different operating systems, and then on top of the operating systems, you will run different applications. So the debugging and tracing getting even more complex. So that's why we are going to talk about CIMICs, which is a full simulation system that can be used to simulate the activities of any electronic system. At the system level, CIMICs, well, first of all, CIMICs itself is a software. We have to remember that. It's a special software that is designed to simulate hardware units, including processors, memory components, peripheral devices, all the components on the motherboard. So what you see here is this is a system level feature of SIMX. It can model multi-core processors and even boards. It can simulate a real-world network connection. It can connect to different process architectures regarding the indentedness word size. You can use checkpoint to trace the execution and also restore from a checkpoint. You can use scripting to automate the debugging process. This is a snapshot of the graphic interface of SIMX, where you can roughly see the configuration of the system. It is a multi-core CPU running a VxWorks real-time operating system, and this is a different one running a Linux WinRiver system. It has different timelines for different software components, kernel and user space applications. This is what you're going to have when you use WinRiver SIMX to simulate your multi-core hardware. So this is SIMX, which runs on top of a regular Linux machine or Windows machine. It has support multi-core hardware, and which runs a WinRiver hypervisor, and on top of that, you can run different OS and applications. So what you see here is the key difference is that we are using SIMX as a simulation tool to simulate hardware rather than execute the real hardware. This brings a lot of benefits. You can have different debugging features. For example, you can do reverse execution. You can trace almost anything. You can set unlimited powerful breakpoints. Repeatability and reverse debugging is very important. You can repeat any run trivially, and also you can stop and go back in time. This is very useful for debugging hardware.